Domela. That's as far as my Zulu goes. And even that I'm not sure about, but goedemiddag, goedemorgen. That was one of the things I liked in South Africa. They come to work and they speak 7, 8 languages. And it still works. As long as Johan tries to start my computer, I refuse to do it with mine because I know I have the same trouble. Good morning. Thanks for coming. Thanks starting. I told Johan nobody's going to come to listen to me that time of the day. But he said, no, there will be people coming. That okay, you're a professor, maybe you bribed them, I don't know. But thanks for coming this time of the day, but it also shows me that there is interest in power quality. I prepared a speech where I have several points where I can stop. And depending how the interest is, how many people fall asleep, I just continue or ask if I should stop. The one thing I would like to ask you, if somebody has really an understanding problem of something, please ask. Because if you don't understand it, trust me, your neighbor is also not understanding it. You're not the only idiot here. Don't feel ashamed. I don't want to have the situation back again. I had in China, dead serious, I gave a seminar, and I felt so proud because every time I asked this Chinese guy, do you understand it? All the Chinese said, yes. Sorry, I was culturally not prepared. Nobody in China says no. And nobody admits that he doesn't understand something. So we had this seminar for 3 days. After day 3, we were also proud. It was several reference, some professor, me, and whatever. We thought we nearly got the guys. They understood everything. And after day 3, one of the guys said, yes, gentlemen, I think I understood everything, but one question. One question I want to ask, what exactly does the word frequency mean? Then you realize there was this poor bugger sitting, sent from their boss to the seminar because there's people coming from the headquarters in Germany. Nobody wanted to go there. Nobody liked to be there. Nobody was interested. Nobody asked the question, so the 3 days were wasted. Please not. If it's a real understanding question, ask. And if you think it's a stupid question, I tell you, you are not alone. Yeah, the Americans did not fly to the moon because they were much more clever than the others. But they were allowed to ask stupid questions. To build a rocket, you need a lot of people asking stupid questions. And if it's something specific about your plant, your situation, let's put it rather to the end. And in the best case, somebody has a scenario where he has a power quality issue. Challenge me, do I find a solution right here? Now, let me start speaking about power quality in general, and then about voltage dips in a little bit more detail. By introducing with a very few words my company, not because it's so important who I am. I'm not a politician, so I'm not advertising myself here. But what we do is highly related to power quality. We're a typical German company. Germany is built around companies like ours. Small, we specialize on one thing. We're not big, we are not rich, we don't have strong finances in the sense of banks behind us. We have strong finances because most of this business in Germany are family owned. We think in generations, not in quarterly plans. I don't give my annual report to nobody. It's for my wife and me. And that's it. We don't have bank debt beside a little bit of mortgage. We invest in the future. We don't take profits out of the company. That is typical German. We're about 55 people now from all over the world. Not from Africa. If I call Jan Hendrik, then it's even one from Africa now. From China, from India, from Eastern Europe, from Germany, local people. It's fun. 20 of them is young engineers. It's a lot of fun working with young people. If you reach my age, you will understand it, because young people tend to think faster than we old ones, and a little bit we gain from our experience. So I enjoyed it. Our customers are all over the world. We're doing about 12 million euro turnover. That's actually something like 80 million. No, bullshit. I'm talking bullshit now. 200 million rand per year. And where we are situated, we are just now busy building a new factory. And when I bought the area where the factory is built, there was an old tower standing. This is an old industrial tower from a factory which was there 100 years ago. And the government offered me 50,000 euro discount on buying the land if I take over the tower as well. And I said, you know what? At least now I can say one thing. It's Donald Trump and me. Huh? Okay, Donald Trump is much richer than I am, but I have much better manners. Huh? And so I thought, okay, that's a deal. Save 50,000 on the ground and buy yourself a historical piece. And it will be, we will build in some offices in 2 years inside the tower to make it our new head office. Now, let me talk on our company, and that is really typical. We focus on one issue, and we have exactly one issue we are talking about, and that is power quality, nothing else. You want to buy a transformer? I can tell you there are certain transformer manufacturers I have good experiences with. You want to lay cable? I can tell you I know that there's books where they write how thick the cable must be, but that's all not our business. Our business is power quality, nothing else. We don't manufacture switch gears, we don't sell transformers. It's purely about power quality. Now, what does power quality actually mean? Power quality is more or less describing one thing. It gives me, according to the IEC standard, the immunity levels my machine must be able to handle. Under which condition must my machine run? Okay? And that immunity level is described in the IEC and also in the South African standards, but as far as I know, the South African standards are very close to the European standards. Technically it makes sense, sorry, it's the same machine, so why should the standards so different? The only people who are a little bit different always are the American and the British. The rest of the world is pretty close to the IEC. So when I always speak about the IEC, this is also covering the most Asian and African standards. Voltage quality or power quality means any deviation of the voltage in height is not wanted. Yeah? Then it can be the voltage waveform, cannot be a perfect sine wave. That's also not wanted. Then, if I speak about the voltage waveform, the IEC standards write about so-called harmonic voltage distortions. That is very clear defined frequency disturbing the net. Typically, for example, the 250 Hertz fifth harmonic voltage as a typical phenomenon. It's also the grid speaks, the standard speaks about non-harmonic voltage distortions. That's everything which is not a multiple of 50, like switching frequency of some semiconductors in the grid, or resonance phenomena are similar. And there's also defined transient overvoltages. That's what the standard is dealing with, and that's what we are dealing with. And to maintain a good power quality is a difficult piece of work. Now in Germany we are lucky, we have a small country with a lot of people. So we have a lot of production and a lot of demand close to each other. Now we're giving ourselves a few challenges with a goal that we want to get rid of all the coal and the nuclear power stations in the next 20 years. That's why we need young engineers to be educated. Besides the fact that we like to kick our butts ourselves, it's not too difficult in Germany, but still there it's a challenge. But now in South Africa, the main producers of coal, correct me if I'm wrong, are somewhere between the Kruger National Park and Johannesburg. That's where the maximum of energy is produced. But that's fair enough when it comes to Joburg. Cape Town is also okay because we have a few power plants there. But what happens to places like the Isco Mining Group? These people are in the middle of nowhere, and they are manufacturing huge amounts of iron ore. It's one of the biggest holes in the world. It's really huge. They have a huge power consumption, but there's nothing around it. Under that circumstances, to maintain a good power quality is not easy. You're facing the same problems like Canada and Russia and other big countries, Saudi Arabia. Same problem, huge power lines, very long distances. And the energy production in Saudi Arabia, lucky enough, you burn the oil where you drill for the oil. It's fine, it's coming close together. But still, it's a huge country, it's Iran, the same huge countries, big challenges. Now, over and above of that, when you love South Africa and you read a German newspaper, normally, to be honest, you only get the shit news. I have to go to a BBC, National Geographic or whatever once in a while to look a movie about lions, the leopards, the giraffes, to remember again that Africa is beautiful. Because the news is terrible. The news is always just the bad part. But obviously, even in Germany, you follow that Eskom has some financial troubles as well. I'm not here to tell the South Africans how to run their businesses. That's not my job. But in Germany and in Europe, we're dealing with a lot of utilities. Germany historically has hundreds of utilities. Not one big one, it's hundreds. And there's one thing that's I'm convinced of. All the utilities we're dealing with, which are run by engineers, are working. And all the utilities I'm dealing with, which are run by politicians, are not working. So maybe, gentlemen, take over again. Electricity is too complicated for politicians. I'm not telling you details. I'm just telling you, try to get Eskom running again by engineers. Doesn't matter if the guy's yellow, white, females, gay, I don't care. But get somebody with an engineering degree. That's the only good advice from my side. We must do, electricity is too complicated for politicians. Yeah? We had a discussions with a politician, just like, yeah?
General Montgomery, when he wrote his book about the history of war, one of his favorite sayings was also, war is too complicated to leave it for politics.
Yeah, it's, yeah.
But there are people that are general.
The people who think they can change Ohm's law are the wrong guys to run a utility. Yeah, so that's my only remark about that. So now power quality. What is power quality? And I put it to structure it a little bit, and we are a company, we are not a university, we are not a scientific institute. We live on selling solutions. Now I structure a little bit, what does power quality mean around the solutions we can have. So, in the standards described, there's certain phenomena of power quality which is now under one. Voltage deviation, voltage dips, voltage unbalance, flicker, over and under voltages. All this have one in common. We're talking the RMS voltage. Just the RMS voltage is too high, too low, it's unbalanced, it's changing too fast, it's changing over the day. For example, in countries like India, we sold capacitors in a 400 volt grid, and there was anything between 280 volt and 700 volt during the day. That's a disaster. But not fast, not dips. Wind, it was a wind park, strong wind, no wind. Strong wind, no wind. Disaster. Flicker, what does flicker mean? Flicker is something you create yourself. If you have a welding machine in the automotive industry which does this bzz, 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 welding spots, every time you do that, your voltage goes down 2, 3, 4%, depending on the factory.
Flickers also created by the type of lighting that you use at the stage of control here. Specifically cause that to pick up off again.
Yeah. But technically for us, the important point, it's a change in RMS voltage. Now all these problems can be solved. And I will speak about that a little bit later in more detail. But just as a memory, all problems in voltage RMS voltage fluctuations can be solved by two ways. Either I push into the grid as much reactive power as I can find, or I put a series transformer somehow in. To simplify it, every problem which is caused by myself, I can fix with reactive power. Every problem which is coming down from upstream, I need a transformer to inject voltage to fix it. I will show you a little bit more detail. So what Johan was also saying, small problems, small voltage fluctuations, which I cause myself, I can compensate with a normal StatCom. I just push in capacitive current. But if it's a 30% voltage dip coming from upstream, there's not much I can do with a capacitor bank. So that's the only question. If you have a problem with the height of the voltage, the only question I ask you, are you producing it yourself, or is it coming from the public grid? If you do it yourself, I sell you some kind of power factor correction, StatCom, capacitor bank, whatever. It's coming upstream. We need a system with a serial transformer. The second big issue, which is now also a very important part of power quality, which is very often underestimated, is harmonics. We see in the most high-tech companies an increase of harmonic distortions. After I speak about what I officially invited for, at the end I will show you a very small example what bad effect voltage distortion can have. Again, if you have a problem with voltage distortions or harmonics in general, the only thing I will ask you before I offer you a solution, I'll ask you more questions, something like, can I have a single line diagram or something like that as well, of course. But the most important question I ask you is, are you causing the voltage distortion by yourself? And do you have any limitations towards the utility, how much harmonic current you're allowed to the grid? If you tell me, yes, my biggest problem is that my utility does not allow me to connect me because I'm creating 600 amp fifth harmonic current, then I will normally try to sell you a current control filter, because say 600 amps the utility is complaining about. Let's try to get 300 out of the equation. Then normally the utility should accept it, or 400. Let's try. I don't have to compensate 600 amps. Okay, 300 is good enough normally, and we are back. We are friends again with the utility. If the voltage distortion by yourself is disturbing you, and you cannot allocate it to one single source like one machine, then I rather would go for a voltage control system. So in one case, I measure the current, I compensate the current. In the other case, I measure the voltage distortion, I put a filter on the bus bar system, and I just correct the harmonics for the whole factory. That's the only thing I will ask you is, do we have to compensate one particular piece of equipment, or do we have to compensate a whole factory? Then, number 3 and 4, which is also power quality. It's also described in the norms, but I must admit in the standards, it's a stepchild. When they wrote about this, the standard, they did not really address that issue good enough. We see, and that's just a practical approach, we see more and more voltage distortions coming from fast switching loads. Nowadays we have megawatt drives with IGBTs 4 kilohertz. And if you run a megawatt drive on a 4 kilohertz signal, you can see a lot of nonsense in the grid. Solar parks, very problematic. You have, what is a typical SMA reactive inverter? Something like 60 kVA, 100 kVA, but there's 100 of them. And they put a lot of high frequency signals onto the grid. That is a very, very interesting phenomenon. The one or the other of you might be confronted in the future that sunny South Africa wants to utilize the sun anymore. Even more, not only for enjoying ourselves, but also for sun power. When you do that, and you have a solar park with 20 megawatt tripping once in a while, then put a piece of measurement equipment that runs up to 20 kilohertz, and send me the measurement data. Then we might find out why it trips, because they tend to disturb each other. Then another phenomenon which is also coming up from a practical point of view, it's one of my favorites. That's resonances in the grid. What is a resonance frequency? I like that to be a professor actually a little bit. Whom of you knows who are the 10 youngest? Must pick one out of them, they're fresh from university normally. Whom of you knows still remembers? You are smiling, you still remember. What is the resonance frequency of a capacitor and a reactor? Omega is?
Omega LC.
Yeah, omega LC, but there's a little bit of formula we need.
Yeah.
It's omega L and C, and what else? Square root, okay? You still remember?
Yes.
Now when I write it down, everybody still remembers. Okay. That's also power quality. Does anybody have a feeling? Now I'm really unfair, I know, but I like it. What is the typical inductivity, strain activity of a transformer 13 kilovolts or 10 kilovolt down to 400 volt 1 MVA? It's unfair, I know. I calculated it myself. It's about 30 microhenry. Okay? And 1 MVA transformer has roughly 30 microhenry strain inductance. Now, if you buy a Danfoss inverter or an SMA solar panel inverter and you open it with a screwdriver or your penknife, it doesn't make you very popular with a customer, you can't close it afterwards again. And you find 6 of this like that on the grid side. What could that be? Okay, now it doesn't come as it's like this. That size, white. What thing could be written on there? Very typical 50 microfarad capacitor for EMC problems on the input side of a drive. Now let's say behind my 1 MVA transformer I have 6 of these drives. Okay, then I have 6 times 50 microfarad. Makes it 300 microfarad. And if I fit that into that formula, I end up with a frequency anything between 1,000 and 2,000 hertz. That is something what we see permanently now. If you have totally unexpected, strange voltage phenomena or trips in your plant, which are not allocated to dips in anything, this might be the reason. This is in the moment my favorite. That also happens. So all these issues are power quality, but today I was asked to focus a little bit on dips and swells. So that is now, we take out of this rather big picture only today solutions for voltage dip, sags, voltage unbalance, and similar. So now, if I look at the situation that my energy supply is not stable for whatever reason, I have a full portfolio on solutions. I would like to go through all of them and try a little bit to emphasize the differences and why we developed our system. That doesn't mean the others are bad. It just means we have different expectations. Now, obviously, when I have the first reaction, if I have a problem with power supply, why don't I put in a UPS system, right? The UPS system is a wonderful system. It can be an online system, it can be an offline system. I take my energy, I charge a battery, and then I supply my load out of a battery. That is theoretically possible. It works in plenty of applications, but according to my practical experience, all the cases wherever somebody tried to run a factory behind a UPS system, it failed. A UPS system, especially an online but also an offline UPS system, has one big disadvantage. The short circuit power goes down dramatically. Your short circuit power disappears. What does it mean, short circuit power? What is the short circuit power of my system? If I have a UPS system, but what is it in your factory? What is short circuit power in your factory? The short circuit current we are talking. If I find an idiot who is stupid enough to do that for me, who's taking a big, what do you call it, not a screwdriver, a spanner. Exactly. Yeah, it takes it, and that's my three-phase copper bus. Bang! When I'm sitting in front of that flash, that's my short circuit power. And as more short circuit power I have, as better it is. I have two advantages. The one is selectivity. My fuses, my circuit breakers, they trip exactly as they are planned to trip. A fuse will blow if the current is high enough. Yes, sir?
I sort of agree with you, but it's common practice to change your protection settings when it's running in the two modes.
Exactly. But that is, have you ever been, I was offered 80,000 euro as a consultant to recalculate the protection settings of a medium-sized German hospital. And I looked at it and said, okay, 80,000 euro for a little bit of consulting work. Sorry guys, forget what I said in the past about strategy for the company. I'm a bitch. For 80,000 euro I do a lot. Trust me. And then I realized how much money it is, or how much effort it is for very little money to recalculate the settings just for a hospital. I'm not saying it's impossible, but it's a huge, huge effort, and sometimes, and that was just a consulting job. But then you have to do it. You have to recalibrate each circuit breaker in your factory. You have to check each bloody fuse if it's still big enough. And that's why UPS system in the most industrial applications does not work. It works very well if I can identify my most important processes, where I say the process controller goes behind a UPS. The IT department goes behind a UPS. But don't ask me to start a large motor behind a UPS. Don't ask me to run a distributed grid behind a UPS. It is very challenging, it's very expensive, you lose the selectivity, and you reduce your harmonic, you reduce your grid your short circuit power drastically. And what does that mean? What is the opposite of short circuit power? Ohm's law, a little bit rewritten. Okay? If I reduce my short circuit power, it means my grid impedance goes drastically up. But so that means my harmonic distortion is just ramping up. We had a case with a German pharmaceutical factory. It was a wonderful thing. They purchased a 5 megawatt UPS system for 5 million euro. And afterward they purchased filters for another €500,000, and another 500,000, and another 500,000. And finally they purchased filters for 5 million. End of story. Now the filters are not running anymore, and the UPS system is not running anymore. It's very difficult to run an industrial process behind a UPS. So okay, then we have other options. What else can we do to make our voltage perfect for our machines? I put in a genset. Sorry, offline UPS, okay, genset, the next. Now, okay, my mistake. I put in somehow transformer which are changing. Now I take either taps on my transformer, I already have. I put in some additional transformers which I switch thyristor controlled, which I can switch with a contactor. All of those things are a lot of these machines you can buy since about 40 years. And I saw them especially in, let's say, emerging countries with very simple industry. These machines are very valuable. If my voltage is changing over the day between us minus 30% till plus 30%, just during the day, due to sunshine and no sunshine, then I can put in such a machine and it works nicely. But normally it does not protect you from voltage dips because the time scale all these machines are working on is seconds, minutes and hours, not milliseconds. Then the fourth system, that is also one Johan meant. What can I do to regulate my voltage? I can push into my grid reactive power. So if my voltage, what does it mean? It's again Ohm's law. If my voltage goes down, I push in capacitive Ohm's current and I raise the voltage. But how much? This is an example for a 1 MVA transformer with a short circuit voltage of 6%. I guess it's similar in South Africa and Europe. That's a standard 1 MVA 6%, 1.25 MVA 6%. That's typical sizes. In the how do you call it? In the housing areas, it's maybe smaller transformers, but in industry, 1 MVA is a typical size. So if I take 1 megawatt inductive load, that would be, for example, the startup of a big motor. Okay, if I start a big motor with 250 kVA or 300 kVA, direct online, then I might have 1 megawatt of inductive load and about 100 kilowatt real power. Now, if I have such a situation, my voltage drops, if it's 1 megawatt inductive load, my voltage drop behind a transformer with an UK of 6% is more or less 6%. It also depends on the grid before and blah, 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 but it's more or less the UK of the transformer. 1 MVA reactive power behind a 1 MVA transformer with a short circuit current of 6%, the voltage drops 6%. That's it, a short circuit voltage of 6%. If I put the same place, not in inductive load, but a capacitor bank, I can raise my voltage. Because my capacitive load has exactly the opposite phase angle to an inductive load. So what will happen is, I raise my voltage. Again, more or less by 6%. So if I can raise with a capacitor bank of 1 MVA behind a 1 MVA transformer, I can raise my voltage by 6%. And that's it. That's the limitation of pushing in reactive power. So if I create my voltage sag myself, for example, my voltage sag is coming from, I'm taking now a real example, I had a discussion with an engineer in South Africa. It's a mining operation, an open pit mine. They have two types of voltage sags. The one is coming from the outside, the typical stuff, some thunderstorms, accidents, blah, blah, blah. What you don't have here in South Africa is snow and ice. But besides that, the reasons are similar to Germany. That's one thing. But the other voltage sag he was creating every time he started his big conveyor belt. They have huge conveyor belts moving material over kilometers. Now when that stops under full load, so, sorry gentlemen, excuse me lady, excuse my French, then the shit hits the fan. To restart the conveyor belt, all those motors, it's hundreds of DC drives, try to start. the voltage goes down. But it's purely reactive power. A motor that doesn't move cannot consume active power. A motor that doesn't move is just a big inductor. So it's purely megawatts. And then I can push in megawatts, I raise the current, and I cure the problem. I don't only fight the problem, I really cure it. Perfect. But it only applies if I'm producing the voltage sag by myself due to my motor start or my welding machine. If it's coming from the outside, because one of those bloody birds doesn't want to take all the shit, sorry again, that's what we have, that's the main cause for voltage sags in Germany. The birds are moving to the south in autumn, and they're coming back in springtime. Now they have their pit stops. They have certain areas where they stop. But you will find, for example, in April, in springtime, German springtime, they're all coming back from Africa, and you find hundreds and thousands of cormorants. It's a beautiful picture. If you're a bird lover, wonderful. There's a lake, hundreds of birds, thousands of birds. It's a fantastic picture. And they sit on the 220 kilovolt lines, all of them, sleeping. And they have one procedure. Every morning they start. They want to fly to Sweden. So if you want to fly to Sweden from my area, that's another 1,000 kilometers to go. The last thing you want to do, I don't want to transport all that shit to Sweden. So every bird that starts, and 1 out of 100, that's where the shit hits the fan. It doesn't hit the fan, it hits the overhead line. Now, one of our customers next to this is running a factory. They are an automotive supplier. Every item that leaves the factory has to do exactly a 24 hours burn-in test. And every morning, exactly 3 minutes past 7, or the next day 5 minutes past 7, when the thermals start, you know, when the air starts moving, all this bird starts and he has a voltage sag. So you have to run a 24-hour burn-in test. And after 23 hours, 56 minutes, the fucking bird is shitting on your overhead line. Huh? Then you take...
Will you if it goes to waste?
Then you take material which is worth 6 million euro, 10 million euro, and you start your bloody test again. It's everything all right. It's okay. There's nothing wrong with that material. But in the norm is written 24 hours, not 23 hours, 56 minutes. I think to the guy, hey, come on, guys. If it's 23 or 24 hours, who cares? He said, listen, can you imagine Volkswagen after the diesel scandal? Now it finds out brakes didn't work because brakes were not tested according to standard. Thank you very much. No way, ever. If it's written in the standard 24 hours, we test it 24 hours. And there's 200 milliseconds missing, and they start from scratch. So that's a typical application that you look for a... Yes? Okay. Oh, okay. Okay. Where is it now? Just a second. I must go back. That's not 100% the right one, but it will work. So voltage sags are really a short-term event that is costing a lot of money, and they're typically, very typically, about 30%. That's why I started my bird story. I lost a little bit more, but I hope I'm back now. They're typically around 30-40%. Why? What happens is, normally the most birds we see, we were sitting there watching that birds. And that is it's in line with our measurements. You get a short circuit between the 110 kilovolt or the 220 kilovolt line, and not the other 110 kilovolt line, but you get a short circuit to the mast. So if one phase against Earth, that's missing. Now we have a lot of transformers from the high voltage to the medium to the low voltage. And each time the phase which is missing is diluted a little bit. So what we see very often, if we miss one phase on the high voltage, we get a voltage sake on the medium voltage or the low voltage side, which is an average between the three phases, about 30%. One phase might be down 50%, another 40%, and another only 20%. But in average, that's the normal voltage sake we see is, in average over the three phases, it's 30–40%. So what we constructed was a system where we put in a serial transformer in the line. Okay? That is just a transformer which is a little bit special. It's a DIII transformer, Delta India, 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 and we put it in line with the grid. So the customer's load would be here, and the grid would be there. Now if a voltage sake, or if the voltage from the public grid goes down, there's inverter here, do we have some pointer? I have those short arms, I will try my very best. Sorry gentlemen, I'm not tall enough, okay? This is inverter here. Has only one goal in his life. The whole processor knows only one thing. Is it here? Oh, wonderful. High tech. If I measure a voltage drop here, the same measurement here, this inverter only knows one thing. My goal is to have the 400 volt or whatever required output voltage here. That's the only thing this inverter knows about the world. My job is to make it 400 volt or 500 or whatever I give to the software here. So if the voltage drop comes, this inverter is injecting a voltage here. If I inject the voltage here, I have it on the other side as well, obviously with a transformed ratio, or with the transformer ratio. I add it to my existing voltage, and the output voltage is exactly 400 volt. Now to do that, this inverter actually has to inject energy in the transformer. Now where does the energy come from? It comes from the DC link. But this DC link is not a capacitive energy storage, it's just a DC link. So in the moment, this inverter is supplying voltage here, the DC link voltage goes down. Now we have a rectifier here, and this rectifier only knows one thing in the world, nothing else. My job is to keep this DC link at the at the right level, which is in this case roughly like something like 700 volt. It's an active rectifier, so even if the voltage goes down, it's drawing actively more current out of the grid, keeping the DC link alive. The DC link supplies my inverter. The inverter pushes it in the serial transformer, and the output voltage is more or less unchanged. Now, that was the idea from the beginning. Why did we want to have a system like this? The only thing we add into the system between input and output is this transformer with a low impedance, so that we keep the short circuit current, the short circuit power high as possible. The impact on the short circuit power is very low. The second is, during normal operation, when there's no voltage sag, okay, I'm running very little energy through my power electronics. There's a little bit of freewheeling current here that also goes to the power electronics, but nothing compared to UPS. The Berkeley University says roughly the average tested UPS they tested really at the university in California is an efficiency of 92 to 94%. That is not the data sheet value of the manufacturer. That is tested from the university. So that means now I have 6 to 8% permanent losses additional. If I run a plant with several megawatt, nobody wants to pay another half a megawatt losses. Even not in America where the power is cheap, definitely not in Germany. Now, so that was the big thing. Do not reduce the short circuit power here. Then when we originally wrote the first, let's say, document where we said, okay, we want to develop such a product, how fast must it be? How fast must the voltage dip correction equipment be? How fast must an active voltage conditioner be? Then we decided for ourselves 5 milliseconds. So we wrote into the documents, we said, okay, the goal is we must be faster than 5 milliseconds. Forget it. Nowadays, 5 milliseconds in power electronics is eternity. The young engineers your age, they look at me and say, boss, hey, 5 milliseconds. I'm talking nanoseconds here. I'm in the gigahertz range, microseconds, but not milliseconds. Forget it. And that's what we did. The first Oscar we built it as fast as possible. And that was a big mistake. Because if you have something that's too fast, it's not stable anymore. What we learned doing that is, if we make our system the fastest we can, we create trouble, because then you switch a capacitor here, just a capacitor bank here, or some machine equipment. Then your system is so fast that it starts to go into interaction with your load. So we had to artificially slow down the power electronics. A lot of people ask me, how fast is your system? It's anything, the maximum time we measure is 2-3 milliseconds, till it's all finished, till the correction is finished. The problem, the challenge was not to make it fast. The problem was to slow it down again. Then we went back to university mentally, and there's a fundamental, let's say, theorem of control mechanisms that speed and stability are excluding each other. If I want to be too fast, my stability goes down the drain. So the only reason why we need 3 milliseconds is because we decided that to make it as long as possible and to make it as slow as possible. Because when we try to be in the microsecond range, what is possible, a lot of strange things happen. You switch your load, your Oscar or whatever, your active voltage conditioner is reacting, and all of a sudden you get fluctuations which are totally terrible. So speed is nowadays not an issue anymore. With the modern IGBTs, with the modern control mechanism, you youngsters know it better than me. How old are you? 30, 28? 30. Sorry, I'm still the Commodore C64 generation, but the young engineers, they all grow up with very high sophisticated software system, very high sophisticated microprocessors. A typical cell phone nowadays is outperforming the NASA in the 60s, by far. So speed is not the issue anymore. Then we had another challenge when we were developing the system, and that is a bypass. The worst thing that can happen to a serial system is if my customer has a short circuit on his side. Okay? For whatever reason, again, some idiot is jumping into the switchgear, a motor has a broken isolation, whatever. In that case, I want to have my short circuit power, my short circuit current fully available, because my blowing fuse is my safety. My circuit breaker must trip by any means. That means my short circuit current must be as fast and as big as possible. In that case, I must do one thing. I must bypass my transformer here as fast as possible. So what we do and that was a challenge. To make the bypass fast was much more complicated than to make the reaction time fast. But what we do, if we detect a jump in current on that side, into the short circuit range, we first use the IGBT inverter to bypass the system. We basically take the 3 bottom IGBTs and make them open, and the top one close. And if you draw a picture for yourself, then you find out that this basically means a short circuit in 3 phases. If I short circuit the three phases of this transformer here, then the impedance of the transformer more or less goes down to zero. My short circuit current can go through. Now an IGBT bypass is a very expensive thing that only lasts for 2, 3, 4 milliseconds. In that time, a thyristor bypass kicks in, and also at the same time, 2 independent mechanical bypasses get triggered. The most important device on our whole active voltage conditioner Oscar is actually a reliable and fast bypass. That is your line of defense. That is human beings' safety. If somebody is putting his fingers in my switchgear for whatever stupid reason, but I saw it, even with experienced electrical guys, people make mistakes, then my fuse and my circuit breaker must trip as fast as possible. And that is something I do not want to prevent. So what we said is, we go into bypass as fast as we can, and that's why we introduced more or less 2 mechanical, 1 IGBT and 1 thyristor bypass, which are independently in control and in technology. That was very important for us. Yeah, if I have a failure on my microprocessor, this bypass is totally independent. So at least we must have 2 software failures in 2 totally independent microprocessors and stuff like that. We don't want to leave everything on 1 microprocessor. I know that those companies, again, I'm sorry, you're just sitting in my line of sight here. You know Texas Instruments and Philips and all those people, I guess. I assume so. I didn't, but my people, my young engineers knew. And they really said, we need this Texas Instrument 65A7. I said, great, buy whatever you want as long as it works. How much does it cost? Oh, $6 if you take an expensive. I said, how much? It doesn't matter today anymore. The microprocessor is nothing. It's peanuts. So that's the system we developed. And we sold it in the meantime several times. It works in the field. We are also ready to deliver the medium voltage solution. We deliver up to 2.5 MVA standard. And now I'm looking for somebody who wants to install it on a 6 kilovolt or 20 kilovolt line, because we're convinced it also works on medium voltage. We anyway need the bypass transformer, need the injection transformer. It doesn't matter if this is a 400 volt transformer or a 6 kilovolt transformer. So that's where we are standing. That's why I was invited from Johan to come to South Africa. I show you a short movie and then I ask you a question. Then we do the exam. No exam. That was bullshit. I hope that works. Where's my sound? Where is my sound? voltage conditioning, when to do it, where to do it, how to do it in different circumstances. I'm open for questions.